Hello, and welcome to another one of our walkthrough videos of exam style questions. We are doing mechanics this time for NCEA Level 2. Let's get into it. Zoom in a bit, make this a bit bigger. So, Jasmine and Ella are on a road trip. They come up to a set of traffic lights. They start at 12.5 meters per second and decelerate at 3.8 meters per second squared. Show that their velocity after 1.25 seconds is 7.75 meters per second. Right, nice achieved question for us to get started with. We know it's achieved because it is a show that question, and this will be just one step to answer this. So let's think about what we've got. We've been given their initial velocity, so VI equals 12.5. We've been given acceleration or deceleration. Now, because it's deceleration, that will be negative. And show that their velocity after 1.25 seconds, at t 1.25, is 7.75 meters per second. So for this, we'll use one of the kinematic equations. So that is going to be VF equals VI plus AT, because we know VI, A, and T. And we want to know VF, which makes this equation perfect. So let's substitute what we know into the formula and calculate it. So 12.5 minus 3.8 times 1.25. Again, the acceleration is negative because it's decelerating. So it's getting slower. And when you put that in the calculator, that comes out at 7.75 meters per second. And again, that is an achieved question. So keep that number in mind, because whenever they give you a show that question in the exam, it's because you'll need that number again later. Okay, on to part B. While waiting at the traffic lights, Jasmine puts the handbrake on so that the car does not roll down the hill. Very smart. The mass of the car and the occupants is 1,750 kilograms. So here's the car, lovely Nissan Leaf. So she's obviously got great taste. And we need to add the vectors onto this diagram. Add labeled arrows to show the forces acting on the stationary car. Well, so we know that there must be gravity. Gravity is always acting, because presumably this car is on Earth. So there'll be a downwards weight force that always acts straight down. Remember, every action is an equal and opposite reaction. That's what Newton taught us. So there must be a support force. And now the support force will be perpendicular, so at 90 degrees to the hill. So that's going to be off at an angle like that. So we'll call that Fs for S support. You could label these as F support and F weight if you wanted to. There'd be nothing wrong with that. And then there must also be a friction force. So let's call that F, holding the car on the hill. Because if there's no friction, it would just slide down the hill. So that is the answer for this part of the question. So you might notice that there is a second part. Complete a labeled vector diagram to show how all three forces act together. So what we want to do is put this into a triangle, and specifically a right-angled triangle. So I'll scroll down a bit. So I've got enough room to do that. So let's start off with the weight force, because that one's going straight down, although that one's very bent. Let's try and make a line that's somewhat straight. Okay, so this one is our weight force. So we know the friction force is sort of up at an angle and the support force is also at an angle. Doesn't matter sort of the order we put them in. You just try and sort of find a way that works for you. But we need to have a right angle in here. So I'll just make that one a bit longer to sort of make it work. So there's our support force and there is our friction force. There we go. So you can see there's our right angle there. Okay, so this is a merit question, these two parts combined. For achieved, correct labeled force diagram. So this one up here. And for merit, correct labeled vector diagram with an obvious right angle. So if you do both of those things correctly, then it is a merit. So let's go on to part C. Show that the value of the friction force required to keep the car stationary is 3,570 newtons. Okay, another show that question. So that also implies that we are going to need that number again in a future question. So keep that in mind. So we've been told the answer, we just need to figure out how to do it. So the friction force. So what we want to do is think back to this diagram here, to our vector diagram. Let's start off with something that we can calculate, which is the weight force. We can work that out because we were told the mass of the car was 1,750 kilograms, and we know gravity is 9.8. So let's calculate the weight force. So weight force is mass times gravity, so 1,750 times by 9.8, and that gives an answer of 17,150 newtons. Force is always measured in newtons. So we can use that to then work out the friction force. If we scroll back up here, we can just about get it all on the screen. Great. So we know that this one is 17,150 newtons. And this angle here is 12 degrees. I would recommend in the actual exam, don't write on this one. Draw yourself another one if you don't want to mess with the one you're going to have marked. So we've got an angle, we've got a side. So let's label these. I've committed to messing up this diagram now, so I will stick with it. Again, don't do this in the exam. So that one is the adjacent, and this one is the opposite. Okay, so we want this one, friction force. So that's opposite the 12-degree angle, and we know the hypotenuse, so we should use sine, because sine is opposite and hypotenuse. So we're going to go friction force, so FF equals FW sine theta. So if you're wondering how we got that, remember sine theta equals opposite over hypotenuse. So H sine theta equals opposite, and it's the opposite side that we want to find. So let's substitute in what we know. We know that the weight force is 17,150 newtons, because we just worked that out, times by sine 12 degrees. And that gives an answer of 3,565, so 3,565.69. Rounding it the same way they rounded it, 3,570 newtons. And that is the answer. So for achieved on this question, you have worked out the weight force correctly, and for merit, the correct answer. Okay, on to part D. While travelling at 100 kilometers an hour, Jasmine sees a pothole in the road 20 meters ahead. She must reduce her speed from 100 kilometers an hour to 80 kilometers an hour to safely maneuver to avoid the pothole. If the time needed for safe braking from 100 to 80 kilometers an hour is 3.4 seconds, show by calculation whether there is enough time to complete braking before reaching the pothole. You should start by showing that 100 kilometers an hour is 27.78 meters per second. It's nice of the question to tell us where to start. Let's do that. We'll also, they haven't told us to do this, but we'll need to work out what 80 kilometers an hour is in meters per second. Okay, let's start with 100 kilometers an hour. So 100 kilometers per hour. Well, if we start by, let's convert that into kilometers per second. So we'll divide it by 60 to convert it into minutes, and then divide by 60 again to convert into seconds. So that would be a 1.67 kilometers per minute, or 0.0277 kilometers per second. And now there's 1,000 meters in a kilometer, so we'll times that by 1,000 to get 27.78 meters per second. So again, just to recap, divide by 60, then we divide by 60 again, and then times by 1,000. You do the same process for 80 kilometers an hour, and that comes out at 22.22 meters per second. So using this information, we now know initial speed and final speed. So she's slowing down from 100 to 80 kilometers an hour, or from 27.78 meters per second to 22.22 meters per second. And we know that to do that safely, that will take 3.4 seconds. So we can use that information to work out how far the car will travel in that time, and whether that is more or less than the distance to the pothole. So distance is VI plus VF divided by 2 times T. We're going to use that formula. Again, we know VI, we know VF, and we know T, and we want to know D. So perfect. So that is going to be 27.78 plus 22.22 divided by 2, and then times by 3.4, and that comes out at exactly 85 meters. So it's going to take 85 meters to slow down safely. So that is the distance required to safely slow. Now the pothole, though, is only 20 meters away. So that is too close. She will not be able to slow down in time. Jasmine will not be able to slow down in time. For achieved on this question, one correct calculation that could lead to a correct solution. For example, correctly changes both speeds into meters per second. So that was up here. For merit, one error, but arriving at an answer for distance, and for excellence, correct answer with explanation and interpretation. So you could, it wouldn't hurt here to add, like, she needs 85 meters, but the pothole is only 20 meters away. Wouldn't hurt to just explain that in depth. Stating the obvious a little bit, but sometimes they like that. Okay, and that is the last part of question 1. Thank you for watching.